And we are back getting ready today to talk about exercise 1.6, which is on higher degree polynomials. So we might be factorizing these, we might be solving these, we might be graphing them. And we also need to know how to deal with these in contexts where we actually haven't been given the equation and we have to work out what the equation is. So the first thing that you need to be aware about when it comes to this topic is the various patterns that I've listed out here. These patterns will not be given to you on the formula sheet at the end of your exam, which means you need to memorize these, unfortunately. So if it's exam 2, I would strongly encourage having these copied down into your theory book, so then you can refer to them. In particular, I struggle to remember this one and this one. That's the sum of two cubes and the difference of two cubes. So we call this one the sum because they're two cubic numbers. A cubed plus b cubed, and this is a difference of two cubes, a cubed minus b cubed. They're the ones that I don't remember. I can remember the other ones okay, but really it depends on you. So if we look over each of these, we've got the first one, which is called a difference of two squares. So again, it's called a difference of two squares because we have a squared minus b squared, like that. The idea is if we have an a plus b times an a minus b, this is the expanded form, it will factorize out like so. So one way that we can double check if that's true is if we just go ahead and directly FOIL it out. So using the FOIL method, what that basically means is we first do the first two terms multiplied by each other. So expanding these brackets, we have a squared, and then we have a times negative b. Don't forget that this is positive b times negative b. So the negative sign comes with it. So this is negative ab, and then we have b times a, which is ab, and then we have b times negative b. So that's negative b squared, because b times b is b squared, and positive b times negative b is b squared. Yeah, negative b squared. So what we're going to notice here is that these two central terms are the same as each other. They cancel out, and we're just left with, as you can see here, a squared minus b squared. Yeah. So that's just quick little proof of that. That's the difference of two squares there. So we call that dots. The second one we have to remember is the perfect square. So this is a plus or minus b squared, and this expands as a squared plus minus 2ab plus b squared. A little note here that you may or may not be aware of. So if you see this notation, plus or minus, basically that means if we have plus, so if it's a plus b, so a plus b squared is going to be equal to a squared plus 2ab plus b squared, right? So if it's plus here, there's a plus over here. And if there is if there's a minus over here, so if this is a minus b squared, then this is a squared minus 2ab plus b squared. So that's essentially telling us that if there's a plus here, there's also a plus here. If there's a minus here, there's also a minus here. In some cases, you're going to see it written a little bit differently. So maybe it says plus or minus on this side, and it might say minus or plus on that side, if this is an equal sign in the middle. In that case, we'd have plus here. If there's a plus here, there's a minus over here. And if there's a minus here, there's a plus over here. We don't have a situation like that over here, but it's just to be aware of. In this case, if this one's plus, this one's also plus. If this is minus, this is also minus. So that's called a perfect square. And we've spoken about that at length in previous years and in previous topics. So next up, we have the two ones that you were introduced to last year. So the first one being the sum of two cubes. So again, we have literally two cubes being added together. And then this one here is called the difference of two cubes because we have a cubed minus b cubed. They expand like this. There are a few ways that we could try and remember that. For example, if we see that there's a plus over here, then we know this is going to be, I guess we can try and write it in this notation over here. So we could write it as a cubed plus or minus b cubed is going to be equal to, well, how do we write this? So if this is plus, this is also plus, and if this is minus, then this is also minus. So that's going to factorize as a plus or minus b. So if that's plus, that's also plus. And then over here, we're going to have, I'll just write in the terms without any signs in between. So notice this is a squared, ab, and then b squared. Now, as we can see here, use a different color for this, just so it's really clear. So like I said, this is plus. If that's plus, that's also plus. If this is minus, this is also minus. And if this is plus, then this one's actually going to be minus. And if this one's minus, that's going to be plus. So it's a little bit like what I was saying before. It's flipped. So I'm going to write it as minus plus. So if this is plus, that's minus, right? And then over here we just have, well, this is always going to be plus. If we have a look, that's plus, it's always plus. So we can just put plus there. And this is a slightly more concise way of writing the sum of two cubes and difference of two cubes formulas, if that helps you. All right, next thing we need to talk about here is what we call binomial expansions. So here we have a cubic expansion. You might call this a perfect cube if you wanted to, just like we call this a perfect square. And it can be written as a cubed plus or minus 3a squared b plus 3ab squared plus or minus b cubed. And again, we know what this plus or minus means now. Now, like I said, you are expected to memorize this, and these ones here are probably going to be the hardest ones for you to memorize. This isn't too bad. So there's a little trick that we can use when it comes to expanding binomials. So we need to remember this formula here, and it looks kind of weird when it's written like this, so just don't let it scare you too much. We have a plus b to the power of n. This is equal to the sum. So this symbol here means the sum of all of the n's from k equals 0 up to n, where n is some number. And we're going to have a to the power of n minus k and b to the power of k. That's a really confusing way of writing this. I think it's much easier to think about this sort of visually, I guess. So you need to remember that whenever we have an expansion, so let's say we're trying to work out what is, let's say, a plus b to the power of 4. We won't go too high. The way this is going to work is the powers of one of them are going to be counting down, and the powers of the other variable are going to be counting up. So, for example, we would have a to the power of 4 plus ab. So this would be to the power of 3. That's the power of 1. So this is like b to the power of 0, which is 1. So you can imagine there's a b to the power of 0 there. Anything to the power of 0 is 1. And then we have times a to the power of 4. Then we have a to the power of 3 times b to the power of 1. Then over here we have a squared and b squared, so both to the same power. And then this is a b cubed, and this will be b to the power of 4. Now, exactly what did I do here? What I'm trying to get across is that one of the variables is counting down. So we have a to the power of 4, a to the power of 3, a to the power of 2, and then a to the power of 0, which is just 1. And then the b's are counting up. We have b to the power of 0, b squared, b cubed, b quartered, b to the power of 4, whatever you would say. That's not all, by the way. So we can see here the same pattern is observed here. We have a cubed, a squared, a, etc. Now, what about these numbers at the front? So where did this 3 come from? So that 3 is actually coming from combinatorics. So this is actually 3 choose 1, I believe this is. And the way that we can remember this is using Pascal's triangle. So this is where the coefficients of the binomial expansion come from, and that's this term here, the n over k. How you can read that is n choose k. So this symbolism, we could say nk with those brackets. That's the same as n choose k. There's a button for this on your calculator, which is quite handy. I'll show it to you real quick. So if I bring up the class pads, we can find this button just over here. Of course, if you have a calculator with you, you could just click expand. It's going to be much faster. But yeah, so if you click, I think it's down in advanced right here. So if we say NCR, we want to work out, say, 3 choose 2, it comes out to be 3. Of course, like I'm trying to get across here, we can just expand this as well using the calculator if we have access to one. So if I wanted to expand a plus b to the power of 4, I can just type that in to the power of 4. I think we need to include brackets around the outside of that. There we go. There's the answer. Now, where does that come from? Well, what we're going to do is we're going to construct Pascal's triangle. I'll just put it over here. So we have 1, 1. Pascal's triangle works where we take the two numbers above a particular digit or a particular entry and we add them together. So this is just going to be a 1 down the side here. Then we're going to go 1 plus 2, which is 3. 2 plus 1, which is 3, and then this is just going to be another 1 over here. So we've always got 1s down the side. Then we have 1. 1 plus 3 is 4. 3 plus 3 is 6. That's a 4. That's a 1 here. So with Pascal's triangle, we're going to look for the row that starts with the power that we're interested in here. So we're interested in the power of 4, which means we're going to be looking at this row right here. This is how we do our expansion. And then all we're going to do is we're going to read those numbers, and they're going to be the coefficients of each of these variables in that order. So for example, the first variable, a to the power of 4, that's just 1. So we just leave that blank. We can write a 1 out the front here if we want to. We don't need to, because if we multiply something by 1, it just stays itself. So we can just leave that. The next entry is 4, so that's the next coefficient. So we're just going to put 4 right here. And then the next one is going to be 6. So I'll just put a 6 right here. Next one's 4. Put a 4 right here, and that's 1. So that's binomial expansions for you. And you can use a similar method to expand any polynomials. All right, so that was quite a long little explanation there. So let's move on and have a few examples. So thing is, we're not always going to have patterns like this. Sometimes we're unfortunately going to have to perform long division, and long division is going to work exactly the same with quartics as it does for cubics. It just takes a little bit longer. You might have to do the same procedure twice. So let's give you a quick example of that. Here's the question. I'll always recommend reading the question at least 2 times when we're doing it. We're going to read it once at the start and once at the end. So it says fully factorize. We have this equation here equals 0, and then we need to solve. So always remember to do both parts of that. Some people might fully factorize and then forget to solve. So just keep that in mind. Okay, so we could use polynomial long division. Polynomial long division is quite a long procedure. So I'm actually going to do this using synthetic division. So just because it's a little bit faster. So how this works is, well, before we do synthetic division, we need to identify a factor. So the way that we do that is, well, this is based on something we spoke about last time called the rational root theorem. We're going to be looking for factors that are equal to some p divided by some q, where p is a factor of the last number here, so the constant term, divided by a factor of the leading term. Now, because this is a monic, which means the coefficient out here is just 1, we only have to consider factors of negative 12. So the possible options for rational roots in this case are just going to be 1, say plus or minus 1, plus or minus 2, because 12 divides by 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, so they're the various factors that we can consider. I will always recommend starting out by considering plus or minus 1 as our initial option. So these are the factors that we want to check. Okay, so let's call this thing equal to px, and I'm going to first consider p of, let's say, negative 1, and let's see if this is equal to 0. Okay, so let's just take negative 1 and put it into this equation. We're going to get negative 1 to the power of 4 minus 4 times negative 1 to the power of 3 minus negative 1 to the power of 2 plus 16 times negative 1 minus 12. So I've just taken that value and I've substituted it in here. So whenever this power is even, it's going to be equal to positive 1. Whenever the power is odd, it's going to be equal to negative 1. That's because, for example, negative 1 to the power of 4, that means negative 1 times negative 1, which is positive 1, times negative 1, which is negative 1, times positive 1, which is positive. So you see it sort of alternates between positive and negative. So this will be positive. This is equal to 1. Then this one over here will be negative, and then we have a double negative, which makes it positive, so plus 4. Then this will be to the power of negative, to the power of an even number, so that becomes positive, and then we have one more negative sign, so that's negative 1 plus, well, that becomes negative 16, negative 12. Very, very easy mistake to make when it comes to getting your negatives wrong. So just be really careful with this. It's a very common mistake. Looking at this, this is definitely not going to be equal to 0. So unfortunately, that doesn't work as a factor. So let's try out another one. Let's have a look at, let's say, plus 1. If we make this plus 1, make this plus 1, make this plus 1, make this plus 1, let's see if that's now equal to 0. So positive 1 squared is equal to 1. This one over here will be negative 4, because that's positive, that's negative. Then we're going to have negative 1, then we're going to have plus 16 and minus 12. Let's put all of this together. Looking at this, we can see that the 1s are going to cancel out. So 1 and -1 cancel out, and then -4 minus 16 is equal to minus 4 minus 12 is equal to -16, which cancels out with this one over here. So now we know that, therefore, I can write, therefore 1 is a factor, which we could also write as x minus 1 in its factorized state. Okay, so now I'm going to just apply synthetic division to this. And I'll just give myself a bit of space. So we can see that's equal to 0. So let's use synthetic division with my factor. I put it out the front. I drop this shape down like this sort of square little box shape. And then we just take those coefficients and we write them out here. So we put 1, we put -4, we put -1. I'll try and make this a little bit neater for you guys. So that's -1, that's 16, and this is -12, okay? And the procedure for synthetic division, the procedure is I'm going to take the first number, let's use red. I'm going to take the first number, drop it straight down. So I drop down this 1 term, it goes here. And then I go 1 times 1, which is equal to 1. I put it here. We go -4 plus 1, which is equal to -3. 1 times -3 is -3. -1 plus -3 is equal to -4. 1 times -4 is equal to -4. Then we have 16 plus -4, which is equal to 12. And then we have 1 times 12, which is equal to 12. And -12 times 12 is equal to 0. And we always should get 0 here at the end if we did this correctly, if this is in fact a factor. If it's not equal to 0, we've made a mistake somewhere along the line. Okay, so what does this tell us? This tells us that we can factorize p such that p of x is going to be equal to, just write out these coefficients. So we're going to have, well, firstly, we take out the linear factor. So we have x minus 1 out the front, and then we have x. So this is going to be, we've got 4 terms. We went down from a quartic, so the next one down is going to be a cubic. So this is x to the power of 3 minus 3x squared minus 4x plus 12. Okay, now I mentioned that sometimes we have to use long division multiple times, and this is definitely one of those cases. We're just going to have to do this again. So the exact same procedure. So if last time we considered p of x to be the polynomial, let's just call this polynomial here. I'll call this whole one here. I'm going to use a different color for it. Let's just call this g of x. We're unfortunately going to need to find another linear factor that satisfies this. Fortunately, we're stuck with the same options for factors because the final term is still 12. Okay, so we've already tried out 1. We know that's not a factor. So why don't we try out plus or minus 2? Let's see if one of them gives us an answer that's equal to 0. So I'm going to use, let's stick with orange for now, just so that this was the second iteration. So just to make this really clear, this was the first iteration of polynomial long division, and this is the second iteration of polynomial long division. Unfortunately, that's just what we're going to have to do with a situation like this. So let's try this out. We're going to need to figure out, is g of 2 equal to 0? So let's take 2 and substitute it into this polynomial over here. I could also put it into the original polynomial. This is just going to be a little bit faster, but both of them should be equal to 0. So I could have gotten this factor first, for example. Okay, so we put in 2 here. This is 2 cubed minus 3 times 2 squared minus 4 times 2 plus 12. Okay, so this is 8. This is 4 times 3, which is -12. This here is -8, and this is plus 12. That's very lucky. I didn't do this before recording this video, so quite fortunately, that and that cancel out, that and that cancel out, and this is equal to 0. Fantastic news. Okay, we found another factor. All right, what does that mean? Well, we're just going to have to repeat the exact same procedure all over again using synthetic division. So we just put it down over here. I'm going to keep using orange just for now. I know 2 is a factor, so I'm just going to stick the factor out the front here. I'm going to put down these various coefficients out here. So 1, minus 3, minus 4, and 12. and then I'm going to go ahead and repeat the procedure from before. We drop down the leading term, the leading coefficient, I guess. So this is 1, we put it here. Then let's see if you can practice this one with me. So what are we going to have to do first? Well, first we're going to take that number, multiply it by that. We're going to have 2 times 1, which is 2. Then we go -3 plus 2, which is equal to -1. 2 times -1 is -2. And then we have -4 times -2, which is equal to -6. And then we have 2 times -6, which is equal to -12. And positive 12 plus -12 is equal to 0. And luckily, the remainder is 0, so we did this correctly. Awesome. We're almost there, would you believe it? So I guess we're up to step 3, and if this was out of 4 marks, we would have gotten only half of the marks, believe it or not. So yeah, let's finish this one up. All right, so what does this polynomial now look like? Maybe we can switch back to blue, maybe. So this is going to be equal to p of x, which is equal to x minus 1 times x, let's read this out. Well, this is going to be x minus 2. That was our second linear factor. And then we have here x squared minus 1 that's minus x. So 1 times x, we're counting down with our powers of x. And then we have minus 6 on the end here. So that's these variables here. Almost done. Okay, last thing we have to do is just fully factorize this. We've gotten this to the point where we've expressed our quartic polynomial as a product of 2 linear factors and 1 quadratic factor. We know how to deal with quadratics. So all we have to do here is now factorize this last bit. And to do that, we can maybe just think of 2 numbers that add to give -1 and multiply to give -6. I'll give you a moment to think about that. So what adds to give -1 multiplies to give -6? I would consider the factors of -6. I would write them out. We could have 1 or 6. One of these is going to be plus or minus. We have 2 and 3. So what combination is going to give us -1? Well, probably it's going to involve 2 and 3. The answer needs to be -1. So maybe this could be negative, and this could be positive. Then we have 2 times -3, which is -6, and 2 plus -3, which is equal to -1. So that works. Okay, so that means that this is going to factorize as x minus 3, x plus 2. And now we have fully factorized the polynomial. Is that the answer? Well, remember what I said at the start. Whenever we get given a question like this, we need to make sure we read the question 3 times. So the idea is read the question, read the question, read the question. We read the question once during reading time. We read the question again right before we do it. We read a question once more after we've answered it. Now, the question says fully factorize and then solve. You would have lost a mark just then. So let's make sure we can solve it. So by solve, all that means is when is this thing equal to 0? When is this thing equal to 0? Because in the original expression, it was equal to 0. So when is it equal to 0? Well, it's equal to 0 when x is equal to 1. Then we have 1 minus 1 equals 0. When x is equal to 2, then we have 2 minus 2, which is 0. When x is equal to 3, 3 minus 3 is 0. And when x is equal to -2. So then that's the ways that we can get 0. And as you can see, that was a pretty easy mark to get, all things considered. And if you're not careful, you can miss out on those easy marks. So just make sure you read the question. All right, so wrapping things up, and then I'm going to do a few more quick examples. I promise to make them quick. We have types of factors. So the first one is called a linear factor. This is when we have, in factorized form, x minus a, and this is when we have a power of 1 out the front here. So for example, if we just have an x in our factorization, so let's say we have a bunch of other stuff factorized, this is going to be called what we call a cut through or a linear factor, and it's going to go straight through like this. So it just goes straight through. We have what's called a touch and turn type of factor. This is when we have power of 2. So for example, x squared, it looks like a parabola. X to the power of 4 also looks like a parabola. It's just going to be kind of like a more sort of squished at the bottom, and then it goes up sharply. So it's going to look something like that. Something like that. Not a very good drawing. But you can see whenever we have an even power, it's going to be this parabola shape, and the higher the power, the more squished and square-like that shape will become. So you can think of this as a touch and turn type factor. And then lastly, we have a stationary point of inflection, also known as a touch, turn, and go through. And that's when it is, say, for example, positive on one side, so positive gradient on this side, positive gradient on that side, and maybe it could be negative gradient on this side, negative gradient on that side. The point is, it's the same gradient on either side, and it goes through like this. So we saw an example of this, or we're going to see an example of this in the next question. So this always happens when we have an odd power of x, which is greater than or equal to 3. Okay, so when it's not equal to 1, in other words. All right, so let's practice this. Firstly, let's see if we can graph this quadratic, this quartic. Well, what even is this? Well, we can see here, this is power of 4, power of 3, power of 2, and power of 1. So this is actually, if we were to expand this out, you can imagine that this is going to be an x to the 4, this is an x to the 3, x to the 2, x to the 1. Multiplied all together, that's actually going to be x to the power of 8. So that's like an octet, I believe, something like that. Okay, so what will this look like graphed? Well, the first thing that we might want to do is figure out what are the x-intercepts. This is probably the easiest thing to do here. X-intercepts occur when y is equal to 0. So we can just make this whole expression equal to 0. And then we can see here, based on the null factor law, this is quite straightforward, we can see that the only way that this whole thing is equal to 0 is if this is equal to 0, or this is equal to 0, or this is equal to 0, or this is equal to 0. So how could that happen? Well, x could be equal to negative 1, then we have negative 1 minus 1. X could be equal to positive 1, then we have 1 minus 1, 0. We could have x is equal to negative 2, then we have negative 2 plus 2, 0. Or x could be equal to 2. And then we have 2 minus 2, 0. Okay, so we found our x-intercepts. Let's locate them on the Cartesian plane. So we have 1 here, we have 2, we have negative 2, and we have negative 1. All right, there they are. Now, let's just quickly pencil in a couple of details about this. First thing is, given that this is an even power polynomial, then because all up, this, like I said, if we were to just expand out the leading values here, this would be x to the power of 4 times x to the power of 3 times x to the power of 2 times x. Is that an octet? No, I don't think it is, because that's going to be 3 plus 4. So I'll just write this out over here. We have 1 plus 2 plus 3 plus 4. What's that equal to? That's going to be equal to... That's equal to 10 all up. Okay, so it is even. All right, well, that means that it's going to look like this. Overall, we're going to go up on one side and up on the other side. How do we know it's not going to be down on one side and down on the other side? Well, that only occurs when the variable is equal to negative 1. When the leading coefficient is a negative value, that's when it's going to be upside down. In this case, we can see that there are no negative terms out the front of any of these expansions, which means that the leading term of the expanded expression is going to be an even number. Sorry, it's going to be a positive number. So that means that on both sides of this graph, we're going to have lines going up like this. So the gradient is going to be negative on this side and positive on this side. Okay, what else do we know about this? Well, this here, this is a linear factor, right? So that's linear. What does that mean? Well, as we saw up here, that means it's going to be a cut-through type cut-through type factor. So at -1, we're going to have a line that is going to go straight through, and we're not really sure if it's going to go straight through like that or it's going to go straight through like that. It's not completely clear yet. I'll just leave it like this for now, and we'll fill it in later. So it's going to be going straight through. That's our cut through. This over here is going to be our, what we called up here, what do we call it? A touch and turn quadratic factor. So this is the quadratic factor. Quadratic factor happens when x is equal to 1. Okay, so that means that at x equals 1, we have a touch and turn type factor. It's going to be like a little parabola like that. Okay, what about this one here? We have plus 2. So again, that's when x is equal to -2. And this is one of those touch, turn, and go through type 1, so what we call a stationary point of inflection, touch, turn, and go through. It's power of 3, or an odd power. So that's when we look over here at -2, and we know that it's going to look something like Well, I guess we can see this is probably even. We can see it has to be negative gradient on this side. So it must go like that and then like that, right? So we have this stationary point of inflection over here. So it sort of goes down, it approaches like a gradient of 0 at the actual x-intercepts, and then it starts out like that on the other side. It's got this sort of weird S sort of shape, or sideways S shape. Anyway, and the last fact we have here is this one over here. So this is a power of 4. What does that mean? Well, that means it's going to be like a parabola sort of shape, but just like a more boxy square sort of parabola. So I'll try and draw a more boxy version of the one that I drew over here. So this is another similar one. Okay, so putting this together, we seem to get a graph that's going to look a little something like this. I don't know exactly what it's going to look like. That will get you almost full marks. The only thing missing is we always need to include our intercepts. So what we'll also need to include here is the y-intercepts. So how do we find the y-intercepts? Well, we need to know when x is equal to 0. That's the value of y corresponding to that is going to be the y-intercept. So if we just take x equals 0, put it in here, we're going to get y is equal to 1 over 10 times, and remember all those x's are just 0, so I can just write the numbers that are left behind. We have 0 plus 1, which is 1. We have negative 1 squared. We're going to have positive 2 cubes, and we're going to have negative 2 to the power of 4. All right, so firstly, we can see that these negatives, that's going to be negative 1 squared, so that's just going to be positive 1, and this is going to be negative 2 to the power of 4. That's also going to be a positive number. So let's just think about what's 1 times 1 times 2 to the cubed. So 1 times 1, that's fine. 2 to the power of 3 is equal to 8, and then we have 2 to the power of 4. That is equal to, well, 8 times 2 is 16. So that's that. And then we need to go 8 times 16, which is the same as, I guess, 2 to the power of 7. This is not one that I have memorized. Yeah, I'll have to look up what this one is. So that's going to be 8 times 16. So that's 128. So powers of 2, useful to know, useful to have them up your sleeve. So that's going to be equal to 128. Don't forget, we're dividing everything by 10. So this is going to be 12.8 in the end. So divide that by 10, 12.8. Okay, so 12.8, it's going to be somewhere around here. So we can just draw our line like this, and just make sure whenever you draw a graph of this nature, we always need to make sure that we label the coordinate pairs of each of our points of interest. So I'm going to label negative 2, 0. Remember to include brackets. They will deduct marks if you don't include those. And we'll have to deduct them in sacks as well. It's important. VCAR's made a point of this. So we need to include brackets. The x coordinate comes first, then the y coordinate. So this is going to be negative 1, 0. This is going to be 0, 12.5. This is going to be 1, 0. And this is going to be 2, 0. All right, so that's how we would draw this graph. All right, another quick example. I'll try and speed through this one. Okay, so we need to graph this in some way, shape, or form. How will this look? Well, what we might imagine here is this is a graph of y equals x minus 1 to the power of 5. This is an odd factor, so we don't freak out when we see a power of 5 there. It's just an odd factor. It's just going to be another touch, turn, and go through type graph. If it was just this, if it was just y equals x minus 1 to the power of 5, the graph would just be over here. We know that will be equal to 0 when x is equal to 1. So we're going to have our factor here, and it's just going to look a little something like that. Okay? So it's going to be that type of parabola, and that type of touch and turn and go through sort of factor. In this case, we do have the minus 32 on the end. So what that does is that actually translates this graph downwards. So you can think of this here as the vertical translation. So this is the vertical translation of this graph. And how that affects things is it's just going to shift the entire graph down 32 units. So where this was up here, this factor, it is actually going to be down here at negative 32. And the only question remaining is what are our x-intercepts and what are our y-intercepts going to be? So firstly, let's find the x-intercepts. So x-intercepts, we need to include these points on our graph. We also need to include our stationary point of inflection. So I should make a point of adding that here. It is going to be at the coordinates 1 and -32, because like I said, it was at 1, 0, and then it got translated down 32 units. So it's down here somewhere. That's our coordinate of stationary point of inflection. Always label them. And then we need to find our x-intercepts. So we let y equal 0. Substitute that in here. We get 0 is equal to x minus 1 to the power of, so x minus 1 to the power of 5 minus 32. Then we can bring this 32 over this side. We get 32 is equal to x minus 1 to the power of 5. Then we can fifth root of 32, which should be equal to 2. And then we see that that is equal to, so that's 2 is equal to x minus 1, which tells us that x is just equal to 2 plus 1, which is 3. Okay, so we have here the coordinate of our x-intercept, which is 3, 0. And then we also need to find the coordinate of the y-intercept. So let's find the y-intercept. Okay, so the y-intercept occurs when x equals 0. So I'm just going to say let x equal 0, substitute that in here. We have y is equal to x, so 0 minus 1 to the power of 5 minus 32. Well, negative 1 to the power of 5, that's just negative 1. Negative 1 minus 32, that's equal to negative 33. Okay, so our y-intercept occurs down here somewhere at negative 30, so that's 0, negative 33. So we can see that our graph is going to have a funny sort of shape where it's going to look a little something like this. Remember, this is a stationary point of inflection. So we have that shape there. And maybe I should try and get rid of this bit over here. So I'll just clear that. I'll just move that down a little bit. So the coordinates of this point are 1, negative 32. We have the shape of a stationary point of inflection. So it looks like that on that side. It looks like that on the other side. It goes up here. And then it goes up there. And let's just imagine this is negative 33 there. I haven't drawn this graph particularly well, but hopefully you can see the key details, which is all you need to label: the x-intercept, the y-intercept, and the stationary point of inflection. To be honest, it is important. They will deduct marks if you draw it like this. So let's try and be as perfect as we can. Given that this is a symmetrical graph, our image does need to be symmetrical. So I shouldn't just say that's good enough. So let's try and make it actually look good. Something like that. It's quite hard to draw with the stylus, but you can see that's the stationary point of inflection. These are the coordinates. Everything is clearly labeled. All right. This is our final question. So again, I'm talking for quite a long time, but let's just finish this up. So we're told here, quartic function, and again, we'll read the question 3 times. I'll read it twice, I guess. Quartic function has the form this. So we have a times x plus b to the power of 4 plus c. These 3 points lie on the graph. We need to calculate a, b, and c. Okay, whenever you have a question like this, just like if it was a quadratic, first thing I would recommend doing is substituting in the coordinate that has 0 in it, because that's usually the easiest one to deal with. So I'm just going to take that 0, substitute it into this equation here. So I'm going to go ahead and sub in 0, 5. So x is equal to 0, y is equal to 0 in this equation. So we have 5 is equal to a times 0 plus b to the power of 4 plus c. And then if we expand this out, we have a times b to the power of 4 plus c. I might just do that over here. So that equals a times b to the power of 4 plus c. Okay. And then we're going to do the same thing here. We're going to substitute this point in. So I'm going to say sub in negative 2, 9. So we're going to replace the y with 9, and we're going to replace the x with negative 2. Negative 2 plus b to the power of 4 plus c. And that's going to be equal to, well, it's going to be quite messy. So we could FOIL this out, or we could use the binomial expansion. Again, it's quite messy. Let's say this is in a tech active exam, by the way. You're not really going to be asked to do this sort of thing in a tech free exam. Just keep that in mind. So again, we'll just substitute this point in here. We have 4, 9. That's going to be equal to 9 equals a times negative 2 plus b. So that should be 4. So 4 plus b to the power of 4 plus c. All right, what do we do next? Well, we can just solve this as a system of simultaneous equations using our CAS calculator. We can go up here, we can click this button, brings up our system of simultaneous equations. So I should say this is a TEC active question, CAS active. Okay, we're going to do that. We're going to just type in these equations. So we need 3 equations. If we click that button one more time, if we're over here, we click that button one more time, it gives us another line. So let's just go ahead, type these equations in. We have 5 equals a times 0 plus b to the power of 4 plus c. Second equation is 9 equals a times negative 2 plus b to the power of 4 plus c. And then last equation is 9 equals a times 4 plus b to the power of 4 plus c. And sometimes it gets fussy if you don't include asterisk signs here, and that might sometimes lead to your calculator crashing. We need to include solve for the 3 variables we're interested down here with commas in between. We click enter, it tells us what the variables are. I am assuming that I've not made any mistakes here, but if I haven't made any mistakes, that tells us that the equation is in fact equal to y is equal to, first variable was a, so that's 1 over 20 times x, and then we have x plus b, so b was equal to negative 1, so this is negative 1 to the power of 4 plus c, which was equal to 99 over 20. Again, assuming that everything here was correct, have we answered the question? Have we? Well, let's have a look. It says calculate a, b, and c and state the equation of turning points. Don't think we've found it. So we've found a, b, and c. We should have explicitly written a equals 1 over 20, b equals negative 1, c equals 99 over 20. So that's not great. We have not stated the equation of the turning point. So again, an easy mark to lose. All we have to do here is look at this. We can see, like I've mentioned before, this is a touch and turn factor because there is a power of 4 here. So that means that this is a turning point, and the value of that turning point, well, it's going to be at x equals 1, and it's been shifted up 99 over 20 units. So just like if this was like a quadratic, you can imagine that this is a quartic that's written in turning point form. So the turning point is simply going to be 199 over 20, assuming that everything was done here correctly. All right, and that's how we work our way through exercise 1.6. I'll try and make sure that the next video isn't quite so long. I'll see you guys in the next video. Have a good one.